Okay, thanks a lot, everyone. So I'm Evan Hirakawa from the USGS in Moffett Field. I'm going to be talking about some work that I've done with Brad Agard on updating the USGS Bay Area velocity model. So Brad did a really good job of kind of introducing the model and talking about the basis and history of it. So that's usually where I start. So I can jump right into the updates to the model. So I came into the USGS as a postdoc in 2018. And my postdoc work kind of resulted in what became the velocity model version 21.1. And that updated version, the 2008 version, which Brad just described. And then now we're working on the version 24, which will update version 21.1. And both of these updates are kind of based on the same idea of running these kind of smaller earthquakes in simulations through the velocity model and looking at synthetic seismograms and observed seismograms, comparing them and trying to, in a nutshell, get the synthetics to look more like the observations by doing some modifications to the velocity model. So I'll show a lot of plots that look like this or like this in this talk. So usually what I'm showing on these plots is an observation, which is a black curve, observed seismogram from some local earthquake, and then on top of that I'm showing some colored seismograms, and usually on all these plots the blue one is some old version of the model and the red one is an updated seismogram with the updated version. So version 21.1 focused on this part of the Bay Area that it's kind of the East Bay Hills, centered around the East Bay Hills, which is this region, but also went into the Livermore Valley and then part up into the Napa-Sonoma region in the North Bay. So that was updated in 2021. Then now in 2024, we're not updating anything that we changed in 2021, but we're moving into kind of the southwest of this area into the more populated part of the Bay Area, which is the the Central Bay region. So in the 2021 update, as I'll kind of describe in this talk, we would kind of use that as a test bed to see, can we just change these kind of velocity versus depth rules that are used to construct the velocity model from the geology model? Can we use these to kind of, the existing rules to kind of swap them in and out and make the synthetic seismograms look better? So Brad showed an equation of one of those velocity depth rules. Here's a couple different ones. So you can see there's different velocity, this is VS versus depth, different curves for different rock types. So there's Cenozoic sediments, there's GVS, which is a Great Valley sequence, then there's higher velocities in the Franciscan Formation, and there's a gabbro layer that has very high velocities. Then in the version 24 update, we're doing something similar, but we had to draw on some more surface geologic data to update the rules instead of just kind of swapping in and out existing rules. So those are the two updates I'll talk about today. We'll start with version 21. So as I said, this kind of centered on this region around the East Bay Hills, and we thought this was an appropriate place to start for a few different reasons. As Brad mentioned, there had been a lot of comments from people like Artie Rogers and Draeger and other people using simulations that there was some kind of discrepancy in the East Bay. And due to the kind of fault distribution around here, we have a lot of different earthquakes of this magnitude kind of surrounding this area. So each of these red stars is an earthquake of moderate, what I call moderate magnitude, somewhere between 3.5 and 4.5. And the black triangles are recording stations, and the green lines are the source to station paths. So you could see in the green, like really green area here, we have very good station coverage to kind of test out the velocity model. We simulate these using SW4, fourth order finite difference code from Lawrence Livermore Lab. And we model each one of these moderate earthquakes as a point source with published NC EDC source parameters, meaning the focal mechanism and the strike and dip. We use a simple triangular source time function where the rise time scales with moment in kind of a Brun corner frequency type formulation. And the reason for trying to emphasize that these are done as point sources is that these are supposedly small enough so that we can kind of assume that most of the complexity going into the simulated motions are coming, not coming from the source. There's hardly any source complexity is the assumption, and that most of it's coming from the velocity model. And so the kind of things that we're looking at when we take a first stab at using the velocity model, so these are the blue lines again are the synthetics using version 8 of the model, the black are the observations. So we see, at some stations the synthetics are too late, or they have too high of amplitude, or some stations there's this really long synthetic ringing that's not seen in the observations. So what kind of changes can we make to the velocity relations that are put onto the geologic model to kind of get rid of these erroneous results? So here's a great example of something really easy to see. So this is a line of stations here on the Berkeley campus crossing the Hayward Fault, which is this thick black line. I'm showing records at these stations from a magnitude 4, I think, earthquake, about 5 kilometers along strike to the southeast from here. And so you can see the stations on the east side of the fault up in the hills, for example, BKS, these stations are the ones that the synthetic seismograms are coming in late compared to the observations. Whereas on the other side of the fault, like for example, BRK, you see very good arrival times. And you can see these numbers here. This is a travel time error. We quantify the travel time error by this kind of cross-correlation procedure. So the black curve again is the observation, the blue is the synthetic wave, and we kind of do a cross-correlation to maximize the sliding cross-correlation coefficient, and then this time lag, we kind of normalize with some arrival time, subtract 1, and the idea is that you get a ratio that's either negative if the arrival is too slow, positive if it comes in too early, and 0 if it's right on time. And so again, the question is, can we just kind of change some of these, raise the velocity on this side of the fault by just reassigning the velocities to these geologic units instead of these ones with higher velocities? And so that's what we do. So here's version 8, the one figure I just showed. Then in version 21, we reapplied a higher velocity rule to everything on the east side of the fault. This is the difference, so this minus this. And now you can see with the updated curves in red, you're having almost like an exact arrival time at a lot of these stations. So again, the travel time error now is 0, which is the second number here. And then this is showing here, kind of zooming out from here, the whole East Bay Hills, where we're kind of showing from a couple different azimuths through the mountains, where we're definitely increasing this arrival time compared to the observation. And then the same thing in the Livermore Valley. But here was the opposite, where the version 8 was giving us arrival times that were too early. So we reduced, the assumption is that the velocities were too high there. We reduced the velocities and the arrival times look a lot better. Another thing, again, that we saw was in the East Bay Hills, we were seeing this long kind of ringing of the synthetic motions that are just not there at all in the observations. So these stations are all here in kind of in between the Hayward Fault and the San Ramon Valley in this kind of sparsely populated area, which we said we focused on. But I'm showing the geologic map because it ties into how we tried to solve this. We plotted a cross-section which is kind of through here. And so what you have between the Hayward Fault and this kind of green unit here is a very low velocity region compared to these high velocities that are in these different regions. And what we kind of started to realize was that this is kind of like this is going to trap seismic waves. This could be kind of like a waveguide. So maybe these waves in here are reverberating through the model and causing this long duration ringing. But then when we compared with the geologic map, in short, we found that this unit that's labeled in the model as Franciscan rock, which has very high velocity, is actually a Great Valley sequence rock on the geologic map. It's more or less mislabeled. So what we did was relabel that essentially as Great Valley sequence and reapply the Great Valley rule. So now you don't have this kind of trapping here. You have seismic waves that are allowed to propagate out into the, further into the east out here. And you see how well this cleans up the synthetic seismograms. And then similarly, like the arrival time, we have some kind of quantitative metric to see how this improves. So I'm using the CAD, the cumulative absolute displacement. So this term is inside the integral is like the vector magnitude of the horizontal velocities. So then integrate that, take the ratio of the synthetic CAD over the observed CAD. So positive values again mean that you're overestimating the CAD. Negative is the opposite. So you can see that with the old version of the model, we had positive values of CAD. Negative value, in the update, we're actually having more negative values, so maybe not such a great improvement, but we're at least getting rid of some of those long reverberations. So as I said, I don't know if I said this, but most of this is published in this paper, Hirakawa and Agard. It's a BSSA paper where we kind of outline more of the updates we did in 2021, and we kind of summarize by showing over the whole domain how these simulation metrics kind of map out through all the paths. So these are kind of like so this map, for example, is showing the stations colored by the travel time error. Blue is too slow, red is too fast. For this particular earthquake, kind of paint these through the source to station path and average over several earthquakes, and then we have kind of an idea of where the discrepancies were. So in version 8, for example, the travel times were slow, blue in the East Bay Hills, and too fast in Livermore. Then we made the changes. See, it's reduced a little bit in version 2021, and then the improvement is basically the difference of these. Green is good, red is bad. So you can see that throughout a lot of these different metrics that we're looking at, the East Bay Hills improved, which was kind of the best part, and then also see some improvement in the Livermore area. So that's version 21.1. Now I'm going to move to version 24, which we're hoping to be released in a few months here. But this is concerned, the last update was, looking at these velocity versus depth rules down to maybe like 10 kilometers. This is just looking at, this version 24 update is just looking at this shallow quaternary geology layer, and this is only on the upper 600 meters. So we're talking about this tan layer here that covers a lot of the Central Bay region. And the velocity depth rules assigned to the quaternary zone look like this. And you can see that it goes down to very low, 80 meters per second at the surface. So we're not missing very low velocities in the San Francisco Bay Area velocity model. But are they correct? So if you see this tan layer spreads all the way up into, the hills here. So maybe this 80 meters per second isn't too bad around the bay, like in the bay mud and stuff. But once you go up into the foothills, if you know this area, this is kind of a hilly area. 80 meters per second does not seem realistic. So take the same approach here. You'll notice that in this, we have a disadvantage that we're not kind of surrounding this area anymore with earthquake hypocenters. We kind of only have events on the Hayward and Calaveras faults. And here we're reducing the VS min. In the last part of the talk, I was using 500 meters per second. Here I'm using 150 meters per second. And we're going down to 25 meter spacing. So we're trying to resolve this layer a lot better. So what we did to affect the velocities in this quaternary layer, we drew on some surface geologic data. So we have these geologic maps of different deposit types. So the purple is like bay mud. All of this stuff is more or less alluvium. Then you have some dune sands and some other interesting deposits. Also, in this area, we have all of these boreholes from Dave Bohr. Well, it's actually from a lot of scientists, from the 70s through the 90s, but I use this database compiled by Dave Bohr, so I cite Dave Bohr. And here's an example of one of the velocity profiles in the black curve. And so what I'm showing here is one station that's in the bay mud out on the Oakland Outer Harbor, and another station that's in the alluvium down here in San Jose. And so it kind of shows what I suggest, and this gray dashed line is showing the velocity depth curve and the velocity model. So it's kind of showing what I suggested, where in these bay mud sites, the velocities aren't too bad, except for this weird kink right here, whereas in the alluvium sites, or often the more coarse-grained units, as I call them, you're having velocities that are way too low compared to the data. So I section off all of these boreholes based on what kind of site they're on. I just chose to simplify these as either fine-grained, coarse-grained, older coarse-grained, and bedrock. Compile all the points as depending on their site type, and plot them, plot each layer, which is just the center, the depth is the center of the layer versus the velocity. And I fit curves, power law curves to these in log space to try to get these new velocity depth versus depth curves. So this is showing an example of them. The blue one is for the fine grain, the orange is for the coarse grain, the black is the current model. So you could kind of see the result I was showing there. Here's the boreholes again with the new relations. So like I said, fine-grained sites, not too much of a change. At the coarse-grained sites, now the new coarse-grain rule fits these velocity logs much better. There's even a site that is actually in mapped bedrock, but on the geologic model, the quaternary zone spreads into there. So we upped the velocities here to those of Franciscan rock. You can see how much of a difference that made. Here's the new velocity model now. The velocity is at the surface, and this is the change in the velocity. So you could see it kind of translated to an increase of velocities over much of this area. So now let's look at some examples of the seismograms from here. This is in the Santa Clara Valley that had a lot of good examples of improvement. Let's look first at the biggest one. This is this station 1862. This station is actually co-located with the borehole I just showed at the Stevens Creek Quarry. So the old synthetics are just wildly overestimating the ground motions because of these extremely low velocities that were in version 21. So once we up the velocities there to more appropriate ones, you could see that the new curve, which is the red line, looks a lot better. And then similarly, in a lot of these stations that are on coarse grain or the older coarse grain rock, you see that in the old model there's just these very high velocity pulses that did not look like the observations that are kind of made to look better in the update. Just some more examples. So out in the San Francisco Peninsula, across the bay, you see the same thing where in some of these coarse grain sites, the velocities were just way too low in the old model. They're fixed now, and the synthetics look more like the observations. Still in this area where we're in kind of this fine-grained bay muck, we're not doing too well, but you could see really and like I said, the seismograms, like the velocity profiles themselves, don't change too much compared to the previous version. Same thing over here. These are out here by the Oakland Outer Harbor. And then the same thing in the East Bay Plain in terms of the coarse grain sites where we're just reducing the amplitudes of the peak motions. This is kind of another summary map, but this time I'm just coloring each station by the average of what I'm now calling a PGV excess. Last time I called it a CAD excess, but this is just the log of the synthetic PGV over the synthetic observed. So positive means the PGV was too high compared to the observed. Those are the red colors. So with version 21.1, you see quite a bit of red all over the place, too high of PGV. These are brought down more closer to what they should be. The white color with version 24. And then this is again showing a difference. So the green is improvement and showing that the PGV is greatly improved throughout much of this area. And then lastly, for all of the records that were on that quaternary zone, I wanted to plot what histograms of what the PGV residual was for both model versions plus the improvement in that. So this is for all of the waveforms. You see version 21.1 is the blue histogram shifted towards the right. So like I said, there's a lot of positive PGV excess. Then with the new model, kind of shifted back towards a mean of 0, which we want it to be. And here, I just point out that really most of our records are on sites with coarse-grained rock. 74% of the records that we have are at coarse-grained sites. So this distribution is kind of really dominated by that. Okay, so I'll finish up. I meant to do a to-do slide, but I didn't add that. So one thing I don't know if Brad mentioned, and what I'll mention is that there have been a few updates, like he said, and like I've been describing, but they've all been kind of just based on reassigning these velocity versus depth rules to the existing geologic framework model. But that geologic model has not been changed since the first version in 2006. So I suggest the next thing we do is to actually go into the Earth Vision software, which is where that model lives, and try to insert some new fault planes and other information that we have. And I'll just leave my conclusions here and stop.